be calculating the electric field strength at this center point right here near this uniformly charged object. And of course, we're going to break that object down into little tiny DQs. So we have a little tiny piece of charge right there. Now, of course, that little tiny piece of positive charge, it's going to have its own influence on this electric field right here, yes? And if you put a little tipsy there, a tiny imaginary positive charge, which way would that tiny imaginary positive charge move due to that little DQ? It would go down this way. So there's going to be a little piece of the electric field going that way due to that DQ right there, yes? But due to symmetry, if we went to the same little piece on the other side over here, another DQ, maybe we can call this DQ1, and we can call this DQ2. Well, due to DQ2, if we go over to here, which way is the electric field strength going to be going due to DQ2? Down this way, yes. So this is DE1, and this would be DE2, and that should be about the same length. Now, since the electric field is a vector quantity, sometimes teachers write out arrows on top of all the vector quantities, so they'll put an arrow over DE because it's a vector quantity. You know, I don't always write that out, but we have to remember the electric field strength is a vector quantity. So if we wanted to know the total electric field strength due to both D1 and DQ1 and DQ2, it would be the resultant of these two. And you could put these two in head-to-tail form and find their resultant. You know, you could just add this one down here. No. And you could see that, oh, which way is the resultant going to end up going? Straight down like that. So that's going to be like the resultant right there. Another way of looking at it, to find that resultant like that right there, we can backtrack here. Forget the head-to-tail. That's so like course B. We could break each one of these down into components, yes? We could say, oh, this one here has a horizontal component like this and has a vertical component like that. This one over here has a horizontal component like this and a vertical component like that. And if we want to know the resultant, we can find the resultant of all four of these components. Well, if you find the resultant of all four of the components, what's going to be the deal with these two horizontal components? They're going to cancel each other out, and in the end, what is the resultant going to be? It's going to be just the good old scalar sum of these two. You can just add these down right here. Yes? So if I call these right here DEX and DEY, we know that the total electric field is the sum, the integral, of all of the little pieces of electric field, of all the DEs. Now, if this here is theta right there, this would be a theta right there. And what we established here is that we don't even need the DEXs because they're going to all cancel each other out for all the different DQs due to symmetry. So we established that this is actually just going to be due to the sum of all of the DEYs. But what can I substitute in for DEY? Yes, I could say, well, that's just the sum of all of the DEs times sign? Yeah, sine theta. And then again, you might be saying, oh look, there's a DE and here's a DE, but you know what we really have to do? Here we have to, we would have to put a vector sign here. So this would be like the vector sum of all the DEs, but we know what it's going to boil down to. It's just going to be down to adding up all the DEYs. But what are all the DEYs? Well, they're the total DEs times sine theta. So this is huge, people. This is like a big trick that we're going to use time and time again as we go through the course. And we need to realize, due to symmetry here, we're not just going to sum up all the DEs. We're just going to need all the Y components. But what are the Y components? Well, they're the total electric field strength times sine theta. So with that said, we begin. Max?
Is the point in the center?
Yes.
So are the two DUIs the same?
Yes.
So is it just going to be like 2 DUI? Like it's not going to be, we're not going to have to use 2 of them?
Yep, it could be 2 DEY, and then you could just do it from here to here. And you could add up all the DEYs on the one side and multiply by 2.
Right.
So that is a true statement. I don't think we're going to integrate it that way. We're going to end up doing the whole shebang thing, but what you're saying is absolutely right. It's all the DEYs on one side,
Right.
added up, times 2. Correct statement. Correct statement. We're not going to make use of that fact. You could. Okay. All right, so let's get started. So we go to the next screen here. So here is my little DQ. And it's the radius R. And what I'm going to have to do, folks, is I'm going to realize that if this here is an angle theta, that little DQ is going to extend the R over and right in here, right in there, folks, that's going to be a little change in angle. It's going to be infinitely small, but nonetheless, that's going to be a little change in the angle, because that little piece of charge, dq, is going to correspond to a little d theta.
So would you integrate 0 to pi?
Exactly. That's where we're going. And you could integrate it from 0 to pi over 2 and then multiply by 2, but that's where we're going. Ultimately, we're going to be integrating this with the dq from 0 to pi. So let's get this party started. So we know that E is going to be the sum, the integral of all of the dE's times sine of theta. But we know that DE from this guy right back here, we know that due to a little q1, this is the electric field due to that point charge. This is the formula for the electric field strength due to a point charge. So coming over here, we could say that DE is going to be equal to 1 over 4 pi epsilon 0, formerly known as K, times, it would be Q1 over R squared, yes? But now it's not Q1, it's DQ. And R is a constant. Yay, R is a constant. So it's capital R squared. And no matter where you are on the rod, it's always the same R. But this whole thing here has to be multiplied times sine theta, because, we know that DE right there, that DE is like this way. there's your DE. But but we're just adding up all the y components. That's where that sine theta came in. Now, I know I didn't write out over here the boundaries, but if I did, I could say over here this is from 0 to the whole electric field, because I'm summing up all the DEs. Normally I don't even write that, leave that off. Well, if I want to add them on here, and again, you could just leave it off. But if you wanted it to be, be complete, if you're going to do this, you need to do it for all of the DQs. So this is a sum for all of the DQs. So this would be from 0 to Q. Again, if that bothers you, leave it off. But again, as I said in the past, most times we're not going to actually integrate over Q, and we're going to substitute dq as something else. So in this case, we're going to use the linear density, and we know that pardon? Just from experience, I know that this is kind of like a line, and we're breaking up into little pieces of the line. So I know it's like we're breaking down the little linear piece.
Why is it not here?
Well, just follow here how it goes, and then we can go back and think about it in terms of area. See if
So you should choose whether it's
Yeah, because that yeah, I don't even really quite know how to answer that. So let's just keep going, and then go in the end and try to figure out how do we see that. So we know that lambda is the linear charge density. It's the charge per length. And if I rewrite that, we know that the charge is equal to lambda times the length. But the length in this case is a little piece of the arc length, because it's a semicircle, yes? And sometimes the arc length is called an S. So that little piece right there is a little piece of the arc length. It's a little ds. So we know that dq, the little piece of q, is equal to lambda times a little piece of the arc length. So instead of calling it a little dl, in this case we're calling it a little ds. But now remember from our rotational motion studies, so we put this on hold here. Remember from our rotational motion studies, what was the hidden relationship between r theta and the arc length s? S equals r theta, bravo. So if s equals r theta, if you have a little piece of the arc length, ds, and r here stays constant, we might as well call this capital R because it's being constant, then we know that a little piece of the arc length, ds, is equal to r d theta. So we're going to make this substitution into the one up above, and then ultimately we get dq is equal to lambda times ds, but what's ds going to be? r d theta. And I knew I wanted to get it into d theta, Cole, because like you notice, I wanted to do 0 to pi. And in order to integrate from 0 to pi, I knew I wanted to go from, all the thetas, doing a d theta thing. So now I have my substitution. And I knew I had to bring theta into this because I had a sine theta there too.
What?
So here we go. I'm just going to bring this down to the next step. So E equals the integral of 1 over 4 pi epsilon 0 times dq. But what am I going to substitute in for that dq right there?
Lambda r d theta.
Right, that dq right there is going to be lambda r d theta. And what is all that going to be over? R squared. And then what else is left?
Sine theta.
Times sine theta. And now that we transform this from a dq to a d theta, we can come over here and say, hey, if we want to cover all of the charge, what do we have to do d theta from? 0 to pi. And now we pull out all the constants, like we can do for integrals. We can pull out the constants. And what are we going to have left here?
Yes, lambda over 4 pi epsilon 0 r. No, lambda is also you pull a constant.
Lambda is also constant, so lambda over
4 pi epsilon 0 r. Yeah, I should accidentally put theta.
because the r squared cancels with one of the r's. Then we have the integral.
Sine theta.
You know what, I'm running out of room there. I should just go to the next line.
D theta sine.
Equals 1 over 4 pi epsilon 0 times r times the integral from 0 to pi of sine theta. Oh, thank you, thank you, thank you. Lambda up here. And the good news is that's not that bad of an integral because we know the integral of sine d theta. What is that? Negative cosine. So this is going to be lambda over 4 pi epsilon 0 times r negative cosine of theta, and our boundary conditions are still 0 to pi. And then if we plug those in, we get pi over 4 pi epsilon 0 r. If we plug in pi, what's cosine of pi? Negative 1. Plus we got the negative 1 out there, yes?
So it's 1.
So it's 1
Plus 1.
minus
Negative 1.
cosine of 0 is 1, but we have the negative 1.
So it's plus 1.
Negative 1. So basically,
It's 2, and then we get
it's going to be 2.
over 2
So
pi.
where am I going to put this? I'll go, and I'll squeeze it right in here. Okay. So the electric field strength at this particular point right there, is equal to 1 over 2 pi epsilon 0 times r. Oh, what else do we have to do though? We can put in this here, right? Yeah. So this is lambda, but what do we know lambda is? I better just write it out. Lambda over 2 pi epsilon 0
Times R.
times r.
Isn't 2m, so that's q over L, and then L
So then we
is
have to put q over L in there. So it's q over L
q over L
over
over
2
2 pi,
pi epsilon 0 r.
and then L is the diameter, I mean the circumference over 2.
Right,
So it's pi
right.
r.
L is going to equal 2 pi r, the circumference, divided by 2. So it's just going to be pi r. So E ends up equaling, what is this going to be?
Q over 2 pi squared r squared epsilon.
Q over L, which is pi r.
Times 2 pi epsilon.
So the pi is going to go down below, right, and get squared.
Yeah.
And same thing with the r.
The r is also
Yeah.
squared.
So it's going to be pi squared epsilon 0 r squared, or
Make it 2. 2 pi squared
oh,
epsilon 0 r
2
squared.
Make it 2
epsilon 0
pi squared r squared.
pi squared r squared.
There's 1/4 epsilon 0, and B is like that's you just do the integral, and then
Yeah,
2 over 4 is
That's
1/4.
it. That is it.
This is cosine of pi negative 1.
Yeah, so
Negative,
the
so
negative,
positive 1.
yeah, so for m to be a negative 1, it's going to be like
1 minus negative 1 is going to be a 2. And then the 2 over that 4